So the backbone is made up of these covalent bonds, and they all have essentially fixed bond lengths, right? So we have a, what is the pattern? A nitrogen to alpha carbon to carbon to nitrogen to alpha carbon to carbon. So you could look up approximate lengths for these bonds in our bond energy and length table that I'd give you if I asked you to, right? You don't need to memorize them. Okay. So for protein folding to occur, we're really only going to rotate about the bonds in the backbone. I don't know why I have this populate one at a time. Here's our backbone, okay? We have 3 different types of covalent bonds. So we have this nitrogen to the alpha carbon is one bond. We have alpha carbon to this carbonyl carbon is another one. And then we have so our carbonyl carbon to the nitrogen, 3 different types of covalent backbone bonds. How come we're going to only rotate the backbone and we're not going to actually break the backbone to get new conformations? Covalent bonds are really strong. It's way too much of an energetic cost to break apart any of those bonds and form rearrangements. Rotations are much easier and lower energy to sort of accommodate. And spoilers, it's going to fold itself in a way that's kind of makes the whole thing at its lowest possible energy state, right? So we saw this word before, the amide plane. Okay, it also includes these carbons, these alpha carbons here. All of these are in the same plane, these 6 atoms. The 2 alpha carbons on adjacent amino acids, this carbonyl and this nitrogen in the peptide bond, this oxygen and this hydrogen. And then this R group, in this case, these both kind of look like they're coming out of the board to me, but they could, they could go into the board. I can rotate this bond here such that this R group would go back if I rotated it sort of into the board. Same thing, if I rotate this bond here, this R group might move around. Like I said, 2 slides from now is a link where I recommend you go there and do some 3D rotations of your own, okay? And while these ones are all flat in the plane of the screen right now. So these 2 bonds here have the ability to rotate, and they could go in either direction, maybe. Okay, the peptide bond does not rotate. The reason the peptide bond doesn't rotate is it has a little bit of double bonded character. Okay, so it's a little bit shorter, a little bit stronger, a little bit restricted. This sort of slight double bond character. Okay? So the peptide bond won't rotate, but the 2 bonds on either side of every peptide bond can. And that's what lets us get into a bunch of different conformations. Okay. So with the peptide bond restricted to a single plane, we have 2 possible conformations. This is poor wording. Because again, these are also in the plane. I guess, they're all in a plane flat this way, but now if you drew a line through this horizontally, which side the alpha carbons are on, so the alpha carbons, again, they're flat in the board right now, but they could be on opposite sides, or they could be on the same side. Is everyone cool with how I'm trying to describe the 3D nature of these things? Okay, so which of these conformations would be preferred and why? Trans conformation, because sterics, it's going to be a lower energy state to be in a trans conformation, right? So again, everything in red is in a plane, flat horizontally, and then whether the alpha carbons are like up or down is what's going on here. And steric repulsion is governing this. So cis and trans are 2 types of conformations. What's an isomer? Yes?
I have a question.
Yes,
so these
absolutely.
trans and cis formations, it won't be the same molecule switching. It'll be like it's formed one way and then it won't change.
Yes, so the ability to form these 2 things is exclusively by the movement of, now again, this peptide bond here is now labeled as omega, and it's a little bit confusing in that it's indicating that like this is rotating, which we don't think of it that way. It's more about orientation-wise, whether they're this 0 degree, are they on the same side for each other, or are they 180 apart from each other, but not because we rotated about the peptide bond. And again, I don't think I ever referred to it as omega going forward.